Welcome back as we continue our example of y double prime minus 2y prime plus y equals e to the x over x squared plus 1. Remember that we solved the homogeneous case and found our y1, y2, and then created our y sub p for our particular solution by multiplying by functions of x, u1 and u2, and then solving those. And I said we were going to make this condition here, u1 prime e to the x plus u2 prime x e to the x equals 0. And in step 4, we found out that u1 prime e to the x plus u2 prime times x e to the x plus e to the x is equal to e to the x over x squared plus 1. Okay, but notice how similar this is to what we did earlier, where we had ax plus by equals p and cx plus dy equals q. If I were to let u1 prime be the x, then the a would act like e to the x. If u2 prime is the y, then b would act like the x e to the x. Similarly, u1 prime again is the x, and c would be e to the x. And if we let u2 prime be the y, then d would be x e to the x plus e to the x. The 0 would be p, and q would be e to the x over x squared plus 1. So in essence, using these two lines here from step 3 and step 4, we've set up a system of two equations and two unknowns. But now these unknowns are functions, u1 and u2, technically u1 prime and u2 prime. So let me pause the page and rewrite those on the top of the next page. Okay, so we've got that written on the top of this page here. And notice that we could write this as a matrix, and the matrix would be e to the x e to the x, e to the x, and x e to the x plus e to the x times u1 prime, u2 prime is equal to 0 and e to the x over x squared plus 1. Okay, and you will see just how that fits with the ax plus by equals little p and cx plus dy equals little q. And so we can solve this. So what we need to do to solve this, the u1 prime guy is going to be the, take the constant column and slap him in place of the first column here. So we'll have 0 and e to the x over x squared plus 1. The second column stayed the same, x e to the x and x e to the x plus e to the x. And we divide by the Wronskian, the determinant of the coefficient matrix, e to the x and x e to the x and x e to the x plus e to the x. But by work we've already done today, we actually found that this determinant, I'll help you quickly remember that this was e to the 2x, okay? Remember that from the front page? Okay, wow, it's like magic. So this guy is e to the 2x. And let's do the top here. So, the first term is going to be just 0 minus x e to the x times e to the x over x squared plus 1. And, this will be really nice. E to the x times e to the x is e to the 2x, so that will divide out. And so we now know that u1 prime is simply negative x over x squared plus 1. Okay, and a similar analysis will show us that u2 prime is equal to, we'll put the e to the x and the e to the x. We don't need to redo the denominator. He's already e to the 2x because he's the same Wronskian guy here. But we put in our constants in the second column according to Kramer's rule, 0 and e to the x over x squared plus 1. Doing the determinant here, we still have e to the 2x in the denominator, and we'll have e to the x times e to the x, which is e to the 2x over x squared plus 1 minus 0, doing our determinant. And once again, ooh, we like this problem. He's not too bad. The e to the 2x's will divide out, and we will get simply 1 over x squared plus 1. Okay. So we now know what u1 prime is and what u2 prime is. So we can take those guys and integrate to find who u1 is. So let's remember that u1 prime is equal to negative x over x squared plus 1. And if I integrate that with respect to x, I will get that, oh, I'm going to use a little substitution. Since I've already used the u letter a lot, I'm going to do a v substitution. V equals x squared plus 1. Therefore, dv would equal 2x dx. And just to make my life a little easier, I'm going to divide by 2 so that x dx will fit perfectly in my substitution. And I will find out that u1, being the integral of u1 prime dx, is going to be equal to negative, this is dv over 2. I'll pull that constant out front, negative 1/2 integral of dv over v, which is negative 1/2 natural log of absolute value of v plus some constant. I'll call that constant, gosh, what should I call that constant? I'll call him K1. But let's look at this a little bit more. So this is negative 1/2 natural log of absolute value of x squared plus 1, which would, plus K1, which is, well, if I take x and he's a real number and I square him and add 1, he can't be negative, so the absolute values won't matter here. So we'll have negative 1/2 natural log of, in parentheses, x squared plus 1 plus K1. Okay. So let's go ahead and find who u2 is. So remember that u2 prime is 1 over x squared plus 1. So if we integrate both sides of that, dx, we will then find out, oh, this is a trig integral, so that u2 is equal to, if you remember your trig integrals, this is the inverse tangent of x. And since he was an indefinite integral, I need a constant, k2. Therefore, our particular solution is going to be u1 y1 plus u2 y2, which is going to be u1 we found out to be negative 1/2 natural log of x squared plus 1 plus some constant, and we're going to times that by y1, which we remember from the previous page. Y1 was e to the x, and we're going to add to that u2, which is inverse tangent of x plus k2 times y2, which was from the front page, x times e to the x. Okay. And recall then also that y sub c was c1 y1 plus c2 y2, or in other words, c1 e to the x plus c2 x e to the x. And notice that if I multiply this together, I get k1 e to the x, but that will be swallowed up in the c1 e to the x. And similarly, k2 x e to the x will be swallowed up in the homogeneous part here, c2 x e to the x. So sometimes you'll see us ignore these constants of integration here on variation of parameters because they'll just work out anyways, and you don't really need them. So we can then make our general solution y equals c1 e to the x plus c2 x e to the x minus 1/2 natural log of x squared plus 1 e to the x plus inverse tangent of x times x e to the x. And there is our general solution.